Hello everyone. Today we are going to start section 8.5 in this video. We'll do page 70 and then the first exercise on the next page 71. Okay, so to begin, we're first going to introduce the notion of a power series. And as you can see here, it looks a lot like the series we've been dealing with, only now we're introducing a variable, the variable x. And so the reason it's called a power series is because, well, it just involves the variable x. And there's a typo here which I'm going to fix and upload to the course Moodle page. But this should be c1x, so it should be c0 times x to the 0, and x to the 0 is just 1, so you get c0 plus c1 x to the first plus c2 x to the second. Then the next one would be c3 x to the third, and so on and so forth. So make sure you download the latest chapter 8 notes to get this fix. Okay, but as you can see, it's essentially an infinitely long polynomial. And so that's why it's called a power series, is just because it involves the powers of a variable x, right? Okay, and anything that does not depend on the variable x, it sort of gets clumped into this Cn, which are called the coefficients of the power series. Okay, so an important thing to remark here is that we can test a power series for where it's convergent, in particular where it's absolutely convergent, or perhaps even just conditionally convergent. And so it'll turn out that a power series can converge for some values of x, but not for others. And in fact, you've already seen this before. If we take the power series, just the sum n equals 0 to infinity of x to the n, you'll notice this is actually a geometric series that we talked about ever so briefly in a previous video. And I said that as long as the absolute value of x were less than 1, i.e. x is strictly between -1 and 1, you just have a geometric series that converges to 1 over 1 minus x, right? Since the power series starts at n equals 0, this is the proper form. You don't need to peel off a factor or anything like that. So we see here that this power series only converges for x strictly between -1 and 1 because it's a geometric series. More generally speaking, power series can look like the sum of Cn times x to the n, but instead of just x to the n, you can essentially shift horizontally where literally it's called the center of the power series is. And so here this is a shift by a units. And so that, like, x equals a would be the center of this power series, whatever that a value is. And so you can see here that when you plug in 0, you get c0 times x minus a all to the 0. Anything to the 0 power is just 1, so you just get c0 plus c1 x to the x minus a to the first, then plus c2 x minus a squared, and so on and so forth. Okay, so if you see a power series that looks like this, though, where you just have an x to the n factor, then its center, notice a would have to be 0, right? And so it's centered at 0. So this one we already know, looking at this power series, it is centered at a equals 0 in this case, right? Okay, so now to test power series for where they converge and where they diverge, the ratio test is going to be your biggest ally here. Let's go ahead and get started. So we're going to apply the ratio test. So we get the limit n goes to infinity, plug in n plus 1, and then divide by plug in just n, or so just as you see it, right? So you get n plus 1 factorial, x to the n plus 1, all over n factorial x to the n, right? And we need absolute value bars around that. Now it's tempting to say everything is positive and just get rid of the absolute value bars, because that's what we did in a previous section. But now notice we have a variable x here, and x could well be negative, right? So we're not allowed to just get rid of the absolute value bars, and that's going to play an important role for us moving forward. So I'm going to group the like things together, right? So the n plus 1 factorial will go over the n factorial. And this x to the n times x to the first will go over this x to the n. Notice here the x to the n's cancel. And I still have this x to the first, so don't lose that. And now I can play that game where I peel off the first factor of a factorial, and then what I'm left with is a one lower factorial, right? So please see the previous video if you need to remind yourself of that. But we see here the n factorial is also canceling. And so notice n is large and positive, so n plus 1 is large and positive. It's not contributing anything negative. So the only thing that could be negative is just the x here. So this is really just the limit as n goes to infinity of n plus 1 times the absolute value of x, right? Okay, now let's see what this is. In this case, we need to do a little something special. In other problems, it'll be a little more straightforward what to do. So if x is dead on equal to 0, then notice that n plus 1 times x, if x is equal to 0, is automatically 0, right? So that would say that the limit n goes to infinity, n plus 1 times absolute value of 0, well, that's just 0, right? And by the ratio test, what does the ratio test say? Well, it says that you need this output to be less than 1, right? So we ask, is this less than 1? Which is yes, and so we get absolute convergence at x equals 0, right? And now if x is non-zero, then notice the absolute value of x will be strictly positive, and you keep multiplying by larger and larger numbers as n gets larger, and so that's actually going to go to positive infinity. So the limit n goes to infinity, n plus 1, absolute value of x will be positive infinity, which is definitely bigger than 1, right? And so this is divergent if x is non-zero. And so you see here, to find all x for which the sum of n factorial times x to the n converges, well, it only converges for literally one x value, namely x equals 0. And so a remark I want to make here, well, what is x equals 0? That's actually the center of the power series. So at the very least, every power series will converge at their center, but it may happen, like in this example, that there are no other x values for which the power series converges. So let's come down here. This one is going to be a little more typical of what you'll see of finding power series and where they converge. So let's first identify the center. Well, if you need to take a peek above, you'll notice that the center is, well, what's the x minus a? So that'll be 3, right? So when a with a equal to 3, that's the center. Okay, so let's apply the ratio test here. And here we're going to do some flipping and multiplying. So we get x minus 3 to the n plus 1 over n plus 1 times n over x minus 3 to the n. I think we're going to stack things that are similar, right? So here I get x minus 3 to the n times x minus 3 to the first over the x minus 3 to the n. And then I'm also going to get this n over n plus 1. Well, this is the limit n goes to infinity. You'll notice the x minus 3 to the n's cancel. That's nice. And so I get x minus 3 times n over n plus 1. And you'll notice that n over n plus 1 for large positive n values is already positive. And so the only thing that could possibly be negative that would need the absolute value is the x minus 3. Okay, and as n goes to infinity, notice this absolute value x minus 3 does not depend on n. The only thing that's changing with n is the n over n plus 1, which goes to 1, and so this limit goes to just absolute value x minus 3, technically times 1, which is just itself, right? And now by the ratio test, let's remember the ratio test is our friend. This is what we're doing here. What does this expression need to be less than for the power series to converge absolutely? Well, we're going to require by ratio test that this has to be less than 1. Okay. Now notice above we didn't have that opportunity, right? It was either 0 or infinity. We couldn't do any sort of arranging for things to happen like that. But now, more typically, you'll be able to arrange this. So let's see what we get here. Well, our center is 3, right? And when you isolate absolute value x minus center less than a number, then that number tells you how far you're allowed to stray from your center. So if I'm allowed to stray 1 unit, that says that I can go as far left as 2 and as far right as 4, right? Because that's 1 unit in either direction. And so everything in the middle is absolutely okay, right? Because it's distance from 3. If you take the absolute value of like 2.5 minus 3, you'll get a number that is less than 1. But the big question marks here are always going to be the endpoints. So let's actually see what happens when we test the endpoints. Well, I mean, we got to do both of them. Let's just do 4 first. So if x equals 4, let's look back at our original power series. We get the sum n equals 1 to infinity. 4 minus 3 all to the n, which is 1 to the n, right? But that is the sum n equals 1 to infinity. Well, 1 to any power is always itself. So this is just the sum of 1 over n. Ooh, this should look familiar. This diverges, right? It's the harmonic series. And so we know that at x equals 4, we don't get a check mark. We're not allowed to use x equals 4, right? Now let's plug in x equals 2. We get the sum n equals 1 to infinity. Now go back to the original power series. If you plug in x equals 2, what do you get? You get the sum n equals 1 to infinity of minus 1 to the n over n. And what do we think about this? Does this converge or diverge? I think it converges. This is a well-known alternating series called the alternating harmonic series. And so we get a check mark at 2. And so all x values for which this power series converges, well, I'm allowed to start at 2 and go up to 4, but I can't include 4, right? And so this is the interval on which our power series converges. All right. And as you can see in the middle of the next page, this is actually called the interval of convergence, and I highlighted that for you. All right, let's look at this one. Where do we think this one is centered? Well, it's just an x to the n, right? So I think this is centered at a equals 0. Okay, so let's see here. We got to apply ratio test. So we're going to get x to the n plus 1 over 5 to the n plus 1 times quantity n plus 1 to the 5th. And then flip and multiply where you just read it as you see it. And so this is the limit, n goes to infinity. Well, let's stack similar things, right? So the x to the n plus 1 I'm going to split as x to the n times x to the first. I noticed there was a tendency for some of you on the homework to use a plus, but that's not right. The proper way to split up an exponential with a plus sign in the exponent is with a multiplication symbol. Okay, similarly, we get a 5 to the n over 5 to the n times 5. And finally, we get n to the 5th over n plus 1 quantity to the 5th. All right, let's see. Well, the x to the n's cancel. The 5 to the n's cancel. So you'll notice I have absolute value x over 5 times n to the 5th over n plus 1 to the 5th, all in absolute values. The only thing that really needs the absolute value here, everything else is positive, so the only thing that needs the absolute value is the x, right? This is the limit, n goes to infinity, absolute value x divided by 5 times n to the 5th over n plus 1 to the 5th. Justify this limit to yourself any way that you like, but n to the 5th over n plus 1 to the 5th is just 1 as n goes to infinity. And so you just get the absolute value of x divided by 5, which, if you'll remember, if I want this to be convergent, ratio test tells me that this limit is required to be less than 1, right? And so you only do this requiring business when you're dealing with power series and finding intervals of convergence. But now look, have I solved for absolute value of x minus the center, i.e. x minus a? No, right? How would I solve this for the absolute value of x? Well, just multiply by 5. So I get the absolute value of x less than 5. Okay, so let's see here. My center I know is 0, and I'm allowed to stray 5 units in either direction. So 5 units in either direction from my center is minus 5 to 5. And now everything in the middle is okay. I just need to check these two endpoints. So pick your favorite one first. I'll start with 5. So let's see. If x equals 5, I get the sum n equals 1 to infinity. Remember, x is 5 now, so I get 5 to the n over 5 to the n times n to the 5th. Ooh, notice these 5 to the n's cancel, right? So this is the sum n equals 1 to infinity, 1 over n to the 5th. And does this converge? I think so. This is a p series with p equal to 5. So I get a check mark over here at 5 as well. Now let's try x equals minus 5. Then I get the sum n equals 1 to infinity, minus 5, parentheses around it to the n. A minus 5 to the n with no parentheses around the minus 5 is technically incorrect. Okay, so you might be thinking, well, I can cancel these 5 to the n's essentially, but you have to be a little bit careful here. So you'll notice that this is minus 1 times 5 all to the n, right? And now using laws of exponents, I can split this as minus 1 to the n times 5 to the n over 5 to the n to the 5th. And now the n to the 5th, or 5 to the n's cancel. And so this is the sum n equals 1 to infinity of minus 1 to the n over n to the 5th. And what do you think? Does this converge or diverge? Well, it's alternating, right? So maybe I can use an alternating test here. What would my bn be? Possibly 1 over n to the 5th. Is bn decreasing? Well, yeah. As n gets larger, you get 1 over larger and larger numbers, which is small. It gets smaller, right? So bn is decreasing, and the limit as n goes to infinity of bn is also 0, right? So this converges by alternating series test. And so I also get a check mark over here. And so the interval on which my power series converges is minus 5 to 5, including the endpoints, which is nice. And like I say, just right here, this is called my interval of convergence, which I denote with IOC, not to be confused with International Olympic Committee. Okay, so let's read this theorem here. For any power series centered at A, there are 3 possibilities. We saw the first possibility with the first example, that a power series converges possibly only at its center. We haven't seen one where the power series converges for all x. Maybe we'll see one later. And now otherwise, there's some positive number r, which was called the radius of convergence, which I denote as ROC, on which the power series converges and diverges if you're far, like outside that radius. Okay. So in this case, what would we? Let's go back and identify all the radii of convergence. So what would the ROC be here? Well, once you solve for absolute value x minus center less than a number, that number is your ROC. So we say r equals 5 in this case. What about here? Absolute value x minus a number less than whatever that number is. Well, in this case, IOC is that, and ROC is just 1, right? R equals 1. And what about this one? Well, this one's a little bit trickier. You only converge at one single point, so you don't really have an interval of convergence. You can think of it as just curly braces, one single point. And the radius, because you only converge at one single point, the radius is defined to be 0, right? You're not allowed any wiggle room outside of your center. You can't move from your center at all. The radius is always telling you how much you're allowed to move at most. Okay, So in the next video, we'll finish this section 8.5.